Hello everyone. Now let's consider about the normal distribution. So in statistics, this normal distribution, or sometimes we call it as a Gaussian distribution, it is a type of a continuous probability distribution. And in most cases, the normal distribution is a very important part of statistics because it's used in, say, social science as well as in many different areas to understand the overall feature of the population as well as the sample. And another reason why it is important because it follows something called a central limit theorem. And we will consider that central limit theorem, what it is in this lecture as well. So basically it states that under some conditions, the average many samples or observations or events of any random variables with a finite mean and variance, this will always converge to a normal distribution. So we are going to consider that is how it's going to reflect in terms of a visual outlook. So once we see this visual outlook, you will have some thoughts on it. So it looks like a so-called the bell curve. Let's directly go on to this part. So you can see this example of this random sample of 100 women here, right? So it's a histogram, simple example in which we have 100 women, and that's a small sample actually. So this bar shows some kind of distribution. You can see it could be the 100 women's height or 100 women's weight. But you can notice that this histogram is kind of bulky and irregular. It's because the sample size is kind of less. So the real data often looks uneven when the sample size is very small. Let's consider the next one, B, where sample size has increased a bit. And if we increase the sample size, this makes the histogram bin more narrow, and the shape is a little bit smoother than that of the A one, right? And the more data, the less randomness. Again, though this is not very irregular, but it seems to be more regular structure, or it looks like it gives us a kind of a bell shape with this histogram, because here the sample size is larger. Let's look into the next one, which is the C part. And here we have a sample size increased quite drastically. And we have also decreasing the class width in this case. So the more the sample width and the histogram, it is more smoother. And now it doesn't look like the kind of a bars. In fact, it looks like a kind of a smooth curve. And this idea of the smooth curve, we call it as a bell-shaped curve. And that's a famous term that we always use in statistics. A normal distribution has a bell-shaped curve in which you can see the middle part is quite high, and both of this right and left is tampered. So as we increase the data, the histogram approaches this stable, predictable curve of bell curve. And of course, you can see this is the normal bell curve for the whole population. We know that when you talk about the population, it includes all individual data points. And at this point, the histogram converge into a perfect, a smooth curve. And you can see there is a perfect symmetry on both sides of the mean. So this red line indicates that it's a mean. So the normal distribution, ideally, it's a mathematical model for many natural and social science phenomena. Let's deep dive into more examples. So we look at these four curves. First, we can see this turtle measurements of the female eastern box turtle. Carapace length is given. Well, we can see this histogram is smooth into the curve and shows how this carapace length clustered around the center value. So you can see the mean value, it's been centered around this mean value. And you can see that only the very few turtles have very short or very long shells. So you can see this tail part is very less turtles over this region. And if you look into this male eastern box turtle, there again the carapace length, if you look at, again, that separates, this curve is quite different from the other one because it actually has a perfect bell-shaped curve. So you can clearly see there is certain differences, but eventually it can reveals that they are normally distributed. And then you have this female eastern box turtle plastral length. This is similar to the one at the top, but only thing is the plastral length, as you can see, is not a perfect curve, a perfect bell curve, but it reflects it still shows us that has the blueprint of a normal curve, you could say. Of course, all of the four has a blueprint of normal curve, but only thing is that this is not as perfect as that of the male one, you can see. And again, there we have the male eastern box pastoral length is there. So there again, you have the kind of a bell-shaped curve, the central around the mean, a little bit edged towards this part, which means very few tails falls on that edge of the right edge, right? But we still have a certain male eastern box on the left edge, but most of them, they are all centered around the mean there. Different groups can have their own normal curve. That's the idea here. Let's move on and see more examples on how these bell curve shapes may look different for different types and norms, and how the relationship between the bell curve can give out the standard deviation and the means relationship. So let's start with the first one here. As you can see, the mean is 3.5, which is at this part, and the standard deviation is 1.5. And as you can see here, the standard deviation clearly shows us the curve gives us how wide the curve could go. This standard deviation is quite high when compared to the other two standard deviation. You can see this standard deviation of 1.5 actually kind of flattens the bell-shaped curve. It actually makes it more wider. So as you can see, the one standard deviation takes you to say around 2 on the left side and 5 on the right side, because we say 3.5 is the mean. So when you add 1.5 to 3.5, it goes to 5. And when you subtract 1.5 from 3.5, it goes to 2. So these are the two inflation points. It's actually, that's where the curve changes its convective. So it changes this part. You can see the inflation happens at this standard deviation. So when you look at the other two, here, this is again a bell-shaped curve, but the standard deviation is only 0.7. So it's 0.7. Standard deviation is 0.7. It's like 3.5 minus 0.7 and 3.5 plus 0.7. So that these are the inflation points where it goes down drastically there. And this is a little bit different from the other curve. And this actually gives us a clear idea about relationship between a mean, standard deviation, as well as the actual shape of the curve, actual shape of the bell curve. As your standard deviation increases, the curve becomes more flatter. And also here, next you have this another point where we have this mean is 1.5 in this example, and the standard deviation is 0.7. So unlike this two, here the mean we have is 1.5. So it's essential. You can see it can really illustrate the location of the mean, can actually determine other information in relation to this curve, but the standard deviation is still remains the same. So, but here what happens is like when you have the mean as 1.5, standard deviation is 0.7. So when you subtract 0.7 from 1.5, it's 0.8, right? So 0.8 on the left side, and when you add when you add 0.7 to 1.5, it is like 2.2 on the right. So those are the inflation point. So it doesn't change the curve, but just the location within this graph, it is being moved. So the inflation point occurs based on the standard deviation. So this is one thing that we can take home from today's lecture, that the mean and standard deviations are related, as you can see. Whenever you say standard deviation, it's a deviation from the mean. And more the standard deviation, it is completely reflected in your curve that you have. Okay, so this is another example. Can you guess like which normal curve has a greater mean among these two, and which normal curve has a greater standard deviation? So that's something that you can take home as you see here. So as you can see, these are the two parts that you have here. And it's clear from the fact that the bell-shaped curve A has a greater mean, because as you can see, it's centered around 15, right? So you should, as we can see, always the normal curve, the center part is your mean. So since the center is 15, you can see it's around at this point, and it has greater mean value. But here you can see the center part for the B curve is 12, right? So it occurs at 12. So that's 12 is less than 15. So here mean is less. But on the other hand, for the B curve, the standard deviation is more because it's more flattened, right? And for the A bell curve, the standard deviation is less. So that's one of the important observation you can take from this particular slide. And there are a few more properties of standard deviation, normal standard distribution. Let's look at it. So here's first part. Always the normal standard distribution has a bell-shaped curve, and the mean, median, mode would be equal if all are centered in the center of the normal curve. Or that kind of normal curve is called the unimodal, where mean, median, mode, if they are all equal, then it's kind of a unimodal normal distribution. And then always normal curve is kind of symmetric. The left side of the curve and the right side of the curve are equal. And the normal distribution is kind of a continuous distribution. It's not about like discrete one, it's a continuous distribution. There's no gaps or no jumps. The curve is kind of smooth. And it also has an asymptotic behavior, actually. So when I say asymptotic behavior, the curve never touches the x-axis to be true. It always, we draw the curve just above the x-axis. So we assume that it goes on forever, kind of from infinity, plus infinity to minus infinity. And the total area under the normal distribution is 100%, or in other words, 1. So that's the key observations that we can have from the basic normal distribution. Let's look at a basic normal distribution curve and try to understand how we can interpret their meaning. So the basic idea here is the mean is located at the center of the normal curve. In this case, you can see the mu. And from mu, if you add one standard deviation or if you subtract one standard deviation. So this is your one standard deviation distribution allocation. So for the first standard deviation, or within one standard deviation from the mean, almost 68% of your population is present. Or in other words, all the 68% of all the data points in your entire sample or the mean is in this first standard deviation for any normal curve. And again, for any standard normal curve like this kind of bell shape, 95% of your population or the data points are present within the 2 standard deviation. You can see mu minus 2 sigma and mu plus 2 sigma, right? So within this range, you can include almost all the 95% of data points are included within that part. And if you include the third standard deviation, it includes 99.7%. As you can see here, mu minus sigma 3 sigma and mu plus 3 sigma, that encompasses 99.7%. Generally speaking, we would just simply say like mu plus or minus 1, mu plus or minus 2, mu plus or minus 3 for representing the first standard deviation, second standard deviation, and third standard deviation. So within first standard deviation, you have 68%. Within second standard deviation, you have 95%. And within third standard deviation, you have 99.7%. It's just like saying, like, if you have heights of the students in the class, say if you have the mean height is like 170 centimeter, and if a standard deviation is like 10 centimeter, you could say from 160 to 180 centimeters, almost 68% students would fall under that category. And 150 to 190 centimeter, which is like 2 standard deviation, within that 95% of the students would fall under this height. And for the third standard deviation, say for example 140 to 200 centimeter, it's almost like practically entire class, right? 99.7% would fall into that category. And there is a chance, right? You see here, when you say 99.7, what about this 0.3%? There is, in certain cases, some unusual chances of having 0.3% outside the third standard deviation. That's very rare occurrence, but it is possible. So this is how within a population you would find that's happening, like 0.3% would happen, generally speaking. So this is the general thought actually. Let's now move on to the next to understand more about this information of standard normal distribution. So area under the curve, as we have seen, it's 1. And you have a z-value formula where z score formula, z equals value minus mean by standard deviation. So in other words, x minus mu by sigma. So let's look into some information on this. So in this case, I will show you how to find the certain values from the z table. If suppose you have a z-score of 1.15, you can go to the z table and you can look at z. This is a z column. The z column you can go for 1.1, but we are looking for 1.15, right? So 1.1, and then for 5 you go like here, 0.05. So it's like saying 1.15. So your value would be 0.8749. This is your z-score based probability value that you have come up with. In other words, we call it as a cumulative area that corresponds to the z-score. In this case, it's 0.8749. We will look into closer. We will see some problems in which we are going to use the table. I will show you in a minute how to bring this about. Okay, here we are asked to find the area under the standard normal curve between z equals minus 1.5 and z equals plus 1.25. So when it comes to minus, we consider the mean part, that is the central part, as 0, and here minus 1.5 and then plus 1.25. So this is your area under the curve that we are interested in this particular example. So we are looking at to understand the basic thought of covering the region between these two z-score value. Let's move on and try to apply it in this problem here. Okay, so your survey indicates that people keep their cell phone on an average of 1.5 years before buying a new one. The standard deviation is 0.25 years. So here, as you can see, the average, which is mean, is given to you, and the standard deviation is also given to us, 0.25. A cell phone user is selected at random. Find the probability that the user will keep his or her phone for less than 1 year before buying a new phone. Assume the length of the time people keep their phone are normally distributed and are represented by the variable x. So specifically, it has given us the information about normal distribution. So we use this problem under normal distribution. So we calculate the z-score first. Mu average value is given, that is mu 1.5, and the standard deviation is 0.25 is also given to us. So let's try to use this information to find the z-score. So z-score is z, and we have to find that a person would keep the phone for at least 1 year, right? So for x equal to less than 1, at least 1 year. So we are looking at least 1 year. So x minus mu by sigma, which is 1 minus 1.15, which is mu, divided by the standard deviation 0.25. So it takes us to minus 2. So when we get the minus 2 value, if you want to look at the probability, we have to go for the standard normal table. So for the standard normal table, it looks like this. Let me show you in a minute. So here it is, the standard normal table. And in the standard normal table, you can go for minus 2. So minus 2 is 0.028. So here's z, and then the points 0.00, 0.01, 0.02 is here. But we are just interested in minus 2.00, so it's just minus 2.0. In this case, its value is 0.0228. So we take that 0.0228 here, and the probability that the user will keep his or her phone for less than 1 year before buying a new one is 0.0228. So it's like 2.28% of cell phone user will keep their phone for less than 1 year before buying a new one. And another reason is like you can see, because this 2.28 is less than 5%, this is kind of an unusual event. So this, if you try to fit into this standard normal curve, as you can see, it is out of those normal range, right? It doesn't fall into the first standard deviation. It doesn't fall into the second standard deviation. In fact, it is a very unusual event. It falls beyond the third standard deviation. Let's move on to this problem here. So in this example, again, we are asked to find the probability for this normal distribution. A survey indicates that each trip to a supermarket, a shopper spends an average of 45 minutes with a standard deviation of 12 minutes in the store. The length of time spent in the store are normally distributed and are represented by the variable x. As shopper enters the store, we are asked to find the probability that the shopper will be in the store for each interval of time listed below. So listed below is like between 24 and 54 minutes, and then more than 39 minutes. So this is our first A problem. The B one is interpret your answer when 200 shoppers enter the store. And then how many shoppers would you expect to be in the store for each interval of time listed below? Again, if 200 shoppers enter the store, we're asked to check how many shoppers would be expected to be in the store between this time and this more than 39 minutes. Okay, let's go on to the first one and see how this would look. The figure here, we are given with figure also, like this figure A, as you can see, it shows us the information about between 24 and 45. So in fact, between 24 and 54, the first part, 24 and 54, and the mu value is 45. And this figure shows you 39 and more. So that area has been shaded for us to understand its pictorial representation. So based on that, we are going into this problem of the first one, A part. So we are given with mu is 45 minutes, and the standard deviation is 12 minutes. And you want to find the area between 24 and 54 minutes. So you're looking at the z-score from 24 to 45 and 54 to 45. So you're looking in from 24 to the mean value. So x minus mu by sigma. So that takes us to minus 1.75 for the z1 score, and for z2 score, 54 minus 45 by 12. So that's 0.75. So the probability that a shopper will be in the store for 24 and 54 minutes is given here. So that's between 24 and 54 minutes. So that's we are just putting in the minus 1.75 and 0.75 here. And we are just manipulating this part for P of Z less than 0.75 minus P of Z less than minus 1.75. So this gives us an idea of how this whole thing is related. So we can look in closer. I will also show you the table from which we can access it for minus 1.75 and 0.75. So for minus 1.7, 5. You can go for the 5. And then you have to also go for 0.75. Okay, so just a moment, let's take it here. Yeah. So for the 0.75, let's look at 0.75. 0.75 is 0.7734. So that's 0.7734 minus, you have a minus 1.75. 1.75 is 0.401. 0.401. Yeah, 0.401. So when you subtract these two, you get 0.773. So based on that, we can actually proceed. So generally speaking, as you know, the whole thing, when you say probability of z less than something, generally speaking, it's like less than infinity actually. So in this case, we are talking about this in both, why do we put up this manipulation part for us to come up with this value. So basically, we can see that whenever you have this probability uh, between two values, in this case, between minus 1.7 and 0.75. So we can't directly look it up. So we have to subtract it. In this case, like this, we have to subtract it. So for example, if you look in this one, P of z minus 0.75. So this gives the total area to the left of 0.75 in a curve. And the same way, if you look in for this one, P of z less than minus 1.75, this gives the total area left of 0.75. So what we need is that if we subtract, what happens is that we are trying to chop off the left chunk to make it easily viewable for us. So it's just like saying if we have this whole part and this goes from infinity to infinity. So if I have this minus infinity over here, and then if we have this middle chunk, which we are interested in, and say this is minus 1.75, and this is 0.75. So total area up to 0.75 is included. Initially, when you say 0.75, what happens is like this whole area, this minus infinity till this part is kind of included. But as you know, what we are interested in is, we are interested in this region between these two regions, right? So if you want to find, or if you want to include this region, what we are doing is that we are actually subtracting, like we are isolating this part. So we have to remove the left part of this 1.75. This region, we have to remove this part. So everything towards the left of this has to be removed. So that's why we put this one here, P of z less than 0.75. You take all things that is left of 0.75, and then you remove this part. That gives us the actual probability. So in this case, when 200 shoppers, when 200 shoppers enters the store, you would expect that 200 times that 0.7333, that is around 146.66. It's around like 147 shoppers would be in store. between this period of 24 to 54. So with the same thought, we can actually try to solve the second questions, which is we are asked to interpret the answer when 200 shoppers enter the store. How many shoppers would expect to be in the store for each interval of time listed below, which is between 24 to 54 and more than, say, 39 minutes. So let's try to figure out this one. Let me erase this first. Let's see. Okay. So here, as you can see, we are looking at this part again, like we have given with mu and the standard deviation. So the area of x greater than 39 minutes, we can actually see that shaded area here, right? More than 39 minutes are given here. So for that, you are calculating the z-score. And once you calculate the z-score, we are again looking for minus 0.5. So minus 0.5 is 0.3085. So for minus 0.5 is minus 0.3085. So we are looking at the probability of shoppers will be there more than 39 minutes. So P of X is greater than 39 minutes. So in this case, we have the probability of Z greater than 0.5. So this is in terms of X, right? X for a period of 39 minutes. But we are looking in terms of z-score, which is 0.5. So 1 minus P of Z less than minus 0.5, which is 1 minus 0.3085. So that takes us to 0.695. So generally, again, with a similar thought that we had earlier. So any cutoff point for Z is minus 0.5. The curve we are splitting into two regions. One is left of minus 0.5 and one is right of minus 0.5. Then we are trying to, so this central limit theorem is kind of central for statistics, you could say, because even if the underlying population distribution is not normal, the sample mean will be normal. So that's very unique about this part. So in either case, the sampling distribution of the mean has a mean equal to the population mean. So always the sample mean is equal to the population mean is one of the assumptions that we make. And the sampling distribution of the sample mean has a variance of 1 by n times the variance of the population, and the standard deviation is equal to the population standard deviation. So as you can see, the variance of the sample mean is sigma squared by n. So as we can see, that's the relationship that we have brought out. The variance is equal to 1 by n times the variance of this population, and the standard deviation equals to the standard population standard deviation divided by the square root of n. So these are the formulas we are going to use for this central limit theorem. And one of the main thing that you have to understand about the central limit theorem is that if the sample size of n is greater than 3, we can always apply this, will always be applicable. And we see if we come to the conclusion that the sample distribution, sample mean distribution follows the normal curve. So as you can see here, there are a few examples shown here, right? So any population distribution, sometimes this population distribution, you can see that n is greater than 30, but as you can see, it's not really a normal curve, right? It's have ups and down, but you do have a mean value over here, and the standard deviation is somewhere, just one standard deviation somewhere here, right? In this two dots represents the standard deviation from the mean. It doesn't look like a normal curve, but when you take a sample from this population, this sample here at the bottom looks like a normal curve. So that is the key idea. So you can take any number of samples you take from the population. All the samples, they look like a normal bell curve. And you can see the mean is in the center and the standard deviation is over here. So this is for any population, given any population, but at times you do have a normal population. So this is a normal population. For normal population also, like sample remains like a bell curve or the normal curve. So this is the basic thought behind the central limit theorem. So with this thought, let's try to look into this problem here. So cell phone bill for residents of a city have a mean of 47 and a standard deviation of 9. So this is shown in this figure. So 47 is the mean. A random sample of 100 cell phone bills were drawn from this population. So from this population, we are drawing some 100 samples. And the mean of each sample is determined. Find the mean and the standard deviation of sampling distribution of sample mean. Then sketch the graph of the sampling distribution. So from this problem, we know that the population mean is given to us, which is 47. So population mean is equal to the sample mean. So that is from the formula here. Sample mean and population mean are the same. So that is 47 in this case. And we are asked to find the standard deviation of the sample mean. So standard deviation of sample mean is population standard deviation divided by root of n. So in this case, population deviation is 9 divided by the root of 100, which is the n, that is sample size. So in this case, we got 0.9. So this is the problem solved it. So as you can see in this example, we are trying to draw the normal curve for the sample mean for 100 individual data points. So 47 is our mean value, and the standard deviation deviates only by 0.9. So it's only 0.9 from the mean. So when you have 0.9, you can see 47 plus 0.9 and 47 minus 0.9. So that's approximately like 48 and 46, you could say. So that's the key part of explanation from this problem of population doesn't look purely bell curve, but the sample looks like. So here's another example similar to the other one. So assume the training heart rate of all 20-year-old athletes are normally distributed with a mean of 137 beats per minute and a standard deviation of 18 beats per minute. So your mean and standard deviation is given for the population. Random sample of size 4 are drawn from this population. So 4 athletes were chosen, and mean of each sample is determined. Find the mean standard deviation of the sampling distribution of the sample mean. So here, this is the population curve, which looks normal, and the mean of sample is same as the population, which is 135. And the standard deviation of sample is nothing but sample of the population divided by the root n. So 18 by 4, which is 9. So when you draw this curve, it looks like here you can see 135 right here as a mean, and the standard deviation is 9 beats. So it's more narrow here. And it is interesting in this problem, actually, the sample size is too tiny, actually. So when sample size is too tiny, like less than 30, for example, sometimes it doesn't follow the normal curve. That's why in the initial part, when we talk about the central limit theorem, if the sample size of n is greater than 30, then we say that it follows the normal distribution. But this is one of the rare example. It still follows a normal distribution. It doesn't happens like this every time. So here is another example. It's quite obvious. From this example, you can straightforward, you can look into the mean and standard deviation. You can calculate the values right there. But only thing is the data are given in this part, like a figure. So figure it shows the length of the time people spend driving each day. So you randomly select 50 drivers from the age of 15 to 19. So from here you select what is the probability that the mean time they spent driving each day is 24.7 and 25.7. So you're assuming that sigma is 1.5. So you're assuming the standard deviation of the population is 1.5 and the sample size is greater than 30 because you have 50 drivers. And based on the sample, central limit theorem, we are trying to proceed with this problem here. So here, what is the mean? What is the probability of the mean time they spend driving each day between 24.7 and 25? So since it falls on this age group, like 15 to 19, so we have 25. So your mu is 25, and standard deviation of the sample, we can calculate it using this formula. Here is more information on how we can actually convert this whole problem. So because we talked about 24.7 to 25.5, so we take Z1 from 24.7 to 25 because 25 is your mean, and then for Z2, 25.5 till 25. So 25 is your mean. So separately, you are calculating the Z-score for each of those point or the limits, because our limit is 24.7 till 25.5. And after that, you go back to this Z table and try to calculate their values again, like for minus 1.47, minus 1.41 and 2.36. So minus 1.41, which is this one here, which is 0.0793 and 2.36. 2.36 is 2.36. 1, 2, 3, 4, 5, 6. It's just this one, 0.9909. So 0.9909 minus 0.073, which is 0.9116. So in this case, you can come to the conclusion that of the sample of 50 drivers, age 15 to 19, about 91% will have a mean driving time between 24.7 and 25.5. So that is 91%. So that's been also shown in this graph here. So we are just implying that this assumption of mu is 25 is correct. About 9% of such sample means will lie outside the given interval, because 91 is within the interval. So the remaining 9% will lie outside the interval. So this is the conclusion of this lecture, in which we discussed about the basic normal distribution. Now you know what is a central limit theorem, what is a normal distribution, what is a bell curve in general, and how it is representing the entire population. Generally speaking, when you have a mean at the center of the curve, as we have seen here, this picture gives us full idea. For one standard deviation, you have 68% of the population is included. For the second standard deviation, you have 95%. For the third standard deviation, you have 99.7%. And in the central limit theorem, our idea is that when you have a sample of more than 30, and you draw a sample. So this sample is drawn from the population. Basically, this sample distribution follows the normal distribution. So that's the idea of central limit theorem. So this concludes our lecture for this normal distribution.